Hello and welcome back to the Geostatistics course for beginners with QGIS and R. This is the lesson 7th of this course, and today we are going to be talking about univariate analysis. At the previous lesson we calculated the median, the mean, the quartiles, the interquartile range, and also we saw how to identify the outliers. If you missed that lesson, you can hit the card located at the top right corner of your screen. Today we are going to start making the definition of expected value, because there is a high relation between the expected value and the mean value. The expected value is the value with the highest probability of occurring. In other words, it is the most probable value that can take a random variable x as a capital letter and is denoted with this expression. If x as a capital letter is a continuous random variable with a probability density function, like this one, then the expected value is defined as follows. The expected value is also known as expectation, mathematical expectation, mean, average, or first moment, and it is the integration in all the range of the probability density function multiplied by x as a lowercase. However, in geoscience, most of the time we don't have the probability density function, we don't have the mathematical expression of this function. Then we cannot use this expression to calculate the expected value. Then what we are going to do is estimate this value with another statistic. In this case, it's going to be the arithmetic average, and that's what we did the other day. When we calculated the mean, we took all the concentrations from zinc. We know they are 155 samples, and then we did the summation of all the samples. Then we divided by 155 and we get the arithmetic average. And that's the way we can estimate this value. But as I said, it's an estimation. When we are doing this statistic over here, we are doing an estimation of this value. Even we are calling both as a mean, these two values are not going to be the same, are different. This one is an estimation of this one, but they are different values. The problem is, as we don't have the probability density function, we cannot make this operation. Then we are using this one because it's easier, because we have a way to calculate that one with our data set, and that's the reason because we are using this statistic. But as we said at the previous video, this statistic is very affected by outliers, and then the mean value is not going to be representative of our data set because it's affected by the outliers. Let's go to see this one with an example. First of all, I would like to talk about the probability density function. At the lesson 5, we created the histogram with the probability density function curve. Is this one. We saw in that lesson that this curve, it was really gross, and it was just an approximation of the probability density function, right? We have this graphical representation of the function, but we have to be aware that this one, it's not the real curve, right? It's just an approximation with the beans, right? And it is really gross. Then what happened here, our mean has to be the value with the highest probability of occurring, right? Then it means that if we take one sample from our data set, the highest probability has to be over here, but that is not right because most of the samples are in this part of the graph. Then in this case, the mean value is not representative of our data set, and that's the reason that when we have a graph like this one, where most of our data is located in this side of the graph, what we have to do is a transformation of our data to make the mean value representative of our data set. As we can see here, right? Here we have a normal distribution of our data, and the mean value is representative of our data, but not in this case. In this case, what we are going to do, but it's not going to be part of this lesson, is a logarithmic transformation in order to move all these values more to the center of the graph, to have a normal distribution of our data. In that case, the mean value is going to be representative of our data set. Then, as you can see, it is pretty important to have a normal distribution of our data, to have statistics that are representative of our data set. Then we saw already different tools to see if our data is normally distributed. The first one was the histogram, where we can see the distribution of our data. As you can see, for example, this one, it's not normal distributed, but here the distribution is pretty normal. Also, if the median and the mean are very close each other, it is indicative of normal distribution. And also, we was working at the previous lesson with the box plot. If we have the box plot quite center in the graph, it's also indicative of a normal distribution. In this case, it's totally opposite. Okay. And also another important thing is if we have outliers just in one side of the graph, it's also indicative of not normally distributed. Let's go to move on to see another important statistic. In this case, is going to be the variance, and here we have the definition. Variance is the expectation of the square deviation of a random variable x as a capital letter from its mean, and it is denoted with this expression. If x as a capital letter is a continuous random variable with a probability density function of fx as a lowercase, then the variance value is defined as follows. The variance is also known as a central second moment. Remember that the expected value, it was known also as a first moment, and the variance is known as a central second moment because of the squared over here, and because if we have a normal distribution of our data, the mean is going to be located at the middle of our distribution. That's the reason, because it's known also as a central. In order to calculate the variance with this expression, it happens the same as with the expected value. In this case, we don't have the probability density function. As we said, in geoscience, most of the time we don't have this mathematical expression, then we cannot calculate this operation over here. Then in order to get an estimated value, what we are going to use is this mathematical expression. And as you can see here, again, in order to calculate the variance, we have also an average, as you can see over here, okay? And that's important because we are using the mean. And if the mean is not good, it's not representative of our data, the variance is not going to be also representative, okay? Hey, do you know the Geo RGB community has a Facebook page? I'm going to leave the link at the video description, then you can click and follow us in this page. I'm going to be posting some content here that you are not going to see on the video tutorials in YouTube. Also, remember, if you want to have access to the scripts that we are using at the course, go to the Geo RGB community website, go to courses, then click on this course, start the course, and then go to the lesson. For example, for lesson 4, click on the lesson, and here you are going to have the attachments related to the scripts that we was using in this lesson. Remember that I'm going to post the scripts exclusively at the Geo RGB website. Okay, let's go to continue. Then the variance is going to quantify how our data is spread with respect to the mean value. I'm going to show you here in a graph. Let's go to imagine that for these three graphs we have the same mean, okay? But the variance is changing. Here we have the mean at the center, and this curve is representing how our data is distributed, okay? All of these curves, this one, and this one, okay? And in this case, for example, what we have is that the values are very close to the mean value. Then in this case we have a very low variance, okay? In this case our data is pretty spread from the mean value to here and also to here, and in this case what we have is a variance that is higher than in this case, okay? And this case is something at the middle between this one and this one. Then we can extract three important things related with the variance. The first one is the variance show how the data is spread with respect to the mean value. The second one is as higher is the variance, less representative is going to be the mean value, because the data, if the variance is really high, the data is really spread, then the mean value is going to be less representative. And the last one is that the variance is always a positive number, because here we are making the square, and it indicates that we are going to have always a positive number. Other important statistic that is associated with the variance is the standard deviation. The standard deviation is the root square of the variance, and one important characteristic of the standard deviation is expressed with the same units as the data, okay? When we are doing the variance, we square the value, and then we are not having the same dimensions as the data, right? Because here we have ppm, it's like we are doing ppm square, right? But when we are doing the root square of the variance, we are going to have the same dimensions as our data, and that is important. But at the end, variance and standard deviation, they are representing the same information. How is the deviation of our data from the mean value? Now I would like to show you another tool that you can use to see a graphical representation of your data that is going to help you to identify if the distribution of your data is normally distributed. That is a QPlot. A QPlot is a scatter plot created by plotting two sets of quantiles against one another. If both sets of quantiles come from the same distribution, we should see the points forming a line that is roughly straight. The most common way of using a QPlot is plotting a normal distribution against the distribution observed in our data. Then, at the x-axis, what we are going to have is the normal theoretical quantiles, and the y-axis we are going to have the sample quantiles. Then we are going to plot all the points, and for example, if we have 50 samples, we are going to have 50 points. And if all the points are on the line, it is indicating that we have a perfect normal distribution in our data. That is going to be equal or very similar to the normal theoretical distribution. Let's go to see an example with the zinc concentration and also with the groundwater elevation, and let's go to see also the script. Now I'm going to load my data. It's going to be this one. It's going to be the Muse and River data set. This one, open. The reference coordinate system is good. Then I'm going to add this one. This one it's okay, and close. going to add a satellite imagery to give some geographical context. I'm going to use the every satellite image, this one, and I'm going to change the color of the dogs for an orange color. Okay, apply and okay. Now I'm going to create a new script. Then I'm going to go here to R, create new R script, and I'm going to paste what I did already. Paste. I'm going to remove this line. We already know about all this stuff. We are going to be using ggplot. We know about this one, and the new things in this script is these two lines. This sentence over here is just to add the line that is 45 degrees that we saw here. I mean, this line over here, this line is making an angle of 45 degrees. And the second part is related with the dots that we are going to add, okay? And that's how we can edit the line, the color, the size, and also for these ones, the geometry we want for the points, the color, and also the size. And for the rest of this script, we know already. That's for the labels. This one is for the themes, for the title, subtitle, and also for the axis. Now I'm going to save this one, and it's going to be saved as number 14, and it's going to be QPlot. Then save, and we can close this one, and we can run the script. Then we are going to go here, this group over here, and it's going to be number 14. This one over here, and here I'm going to add the parameter syn. The X label is going to be normal theoretical quantiles. For the Y axis is going to be observe quantiles sync in ppm. The title of the graph is going to be QPlot, and for subtitle is going to be raw data. I'm going to pass the video faster. Then I'm going to save this one as a QPlot. Save, and I'm going to run the script. Now let's see how we can make an interpretation of this graph. First, let's go to make this screen bigger. I mean the graph. And as I said, at the y-axis we have the normal theoretical quantiles. At the y-axis we have the observed quantiles for the zinc concentration in ppm. We have a total of 155 points because we have 155 samples. We have 155 different values for the zinc concentration. Also, the range here goes from 0 to 1,800 something. This one, there is no negative numbers. This part of the graph, it represents the tile of the distribution of our samples. And as you can see, most of the points are out of the line. This kind of morphology of the points is indicating that the distribution of our data is not normally distributed. We have some of the points over here on the line, but that is not really representative. Now I'm going to do the same exercise, but I'm going to use the groundwater elevation, where we have the data more normally distributed, and then we can see how the QPlot looks like. I already loaded the data related to the groundwater data set, and also I fill all the information to make the QPlot, and now I'm going to run the script. Now we can see this one, and I'm going to make the screen bigger. In this case, we have here the quantiles associated with the groundwater elevation in meters, and here we have the normal theoretical quantiles as the other graph. In this case, we have 57 samples for the groundwater elevation, and as you can see in this case, most of the points are very close to the line or on the line, and that is indicative of a normal distribution. Also for the tails, as you can see over here and over here, it is not really bad, okay? As you can see, there is a big difference between this graph and this one, okay? And if we check the histograms, this one is for the one is not normally distributed, and it's related with the zinc concentration. As you can see over here, zinc concentration, and this one is normally distributed, and that one is for the groundwater elevation, and that's the difference that we can see between the QQ plots. Well, that's the end of this lesson. Thank you very much for watching, and see you on the next one.